How do computers multiply two numbers? Computers perform multiplication using a binary multiplier, which is similar to the one we were taught in school, except where the numbers are in binary, that is, in zeros and ones. One best example of a binary multiplier is the Wallace tree multiplier. Wallace tree was designed by an Australian computer scientist, S Wallace. He is best known for principle of minimum message length, Wallace tree multiplier, random number generator, and hardware for detecting and counting cosmic rays. In this video, let's implement a 3-bit multiplier that uses the Wallace tree reduction technique to produce a 6-bit output. The reduction takes place in 3 stages. Partial product generation. In this stage, each bit of one argument is multiplied by each bit of the other argument. 2. Partial product addition, where the number of partial products is reduced to 2 by layers of half and full adders. 3. Final addition stage. In this stage, the resultant values from previous stages are added with a conventional adder. Let us look at an example to understand this. Initially, two 3-bit numbers are multiplied with each other to give 3 partial products, blue, green, and orange. The 2 partially generated products from step 1 are added to give a single bit, represented as cyan in step 2. As in step 3, when a carry is generated, it is appended to the continuation bit. These additions are held until all the bits and carries have been processed. In other words, the process stops when 2 bits are left out. At this point, in step 6, the process ends. Thus, to multiply the bits, an AND gate is required, while for the addition, adders are used. Additionally, an XOR gate is required to implement the adders. The Wallace multiplier is built using all these components. Here I shall be using eSim as a workspace. eSim is an open source EDA tool which is integrated with KiCad and NGspice to design and simulate a circuit. AND gate. The output of AND gate will be high when both the inputs are high and low for other cases. To use our AND gate in other circuits, it has to be defined as a subcircuit. A subcircuit is mapped to a component symbol which can be used in other projects. To create a subcircuit, select Subcircuit from the eSim workspace, then click New Subcircuit. Arrange the NMOS and PMOS transistors for AND functionality and wire them up. Then check for the DRC errors. If none, proceed to generate the SPICE netlist. Now, to use this subcircuit in the future schematics, we have to assign it to a component symbol. Let us draw a component symbol for AND gate. From the schematic toolbar, go to Library Editor. Select the current library as eSim subcircuit and draw a new component symbol. Similarly, we have to assign the subcircuit and a component for the XOR gate. XOR gate. The output of XOR gate is low when both the inputs are similar and high when the inputs are opposite. Perform the steps mentioned in the previous method to design the subcircuit, a component, and then generate the SPICE netlist. We can now design a half adder circuit. Half adder. It has 2 inputs and 2 outputs. The output sum of a half adder is high when both the inputs are opposite. The output carry is high when both the inputs are high. Draw the schematic for half adder using AND gate and XOR gates. Annotate and perform the DRC. If none, then generate the SPICE netlist and make a component symbol for the half adder. Full adder. It has 3 inputs and 2 outputs. The output sum is high when the odd number of inputs are high. The output carry is high when 2 or more inputs are high. Draw the subcircuit schematic and a component as mentioned in earlier topics. 3-bit Wallace multiplier. Draw the schematic for a 3-bit multiplier using AND gates, half and full adders. The schematic has 3 bits for input A, which are A0, A1, A2. 3 bits input for B, which are B0, B1, B2, and 6 bits for output Z, which are Z0, Z1, Z2, Z3, Z4 and Z5. Annotate the schematic and perform a design rule check for any errors. If none, proceed to generate the SPICE netlist. Now convert the KiCad to NGspice netlist. In the subcircuit section, add the path of the subcircuits for AND, XOR, half adder and full adders. Then click Convert, which shall display the successful conversion. We can now test the multiplier circuit with NGspice simulation. Open the terminal, change the directory to Wallace33. To keep things neat and clean, let us make a copy of wallace33.cir.out and rename it as _test.cir. Do these changes to use Sky130 PDK. In the subcircuit files of AND and XOR gates, rename the properties of MOSFET N and MOSFET P for their respective Sky130 names. Now add the path of Sky130 library inside the test file. Generate the input signals A and B using the pulse signal. Then perform transient analysis and plot the inputs and outputs. Type NGspice followed by the CIR file name to simulate using NGspice. Now wait for some time to get the waveforms. You can observe that for input A0, A1, A2 being 1, 0, 1, B0, B1, B2 being 0, 1, 0, the output Z is 0, 0, 1, 0, 1, 0. This verifies our multiplier circuit. In the same way, you can change the input signals A and B inside the test.cir file and observe the output Z. This completes the simulation. You can find all the resources used in this video under the description. If you find this video useful, please like and subscribe. Thank you for watching.